Hello and welcome back. In this video, we'll be looking at section 1.3.3. We want to talk about the relationship between spans and subspaces. Our goal is pretty straightforward. We want to show that any span is a subspace and that any subspace can be written as a span. Right? So let's state and prove theorem 1.3.1. We'll be saving the examples for the next video. All right, so let's take V to be any vector space. I'm going to take S to be any subset of V. Then span of S is a subspace of V. In fact, it is the smallest subspace. Sorry, low on space. I want to write smallest subspace. So smallest subspace. Smallest subspace of V, which contains S. All right, and then if W is a subspace, then I can write W as the span of some set S for some subset S in V. All right, so let's prove this. I'm going to start by proving that span of S is a subspace of V. So that's part one. Part one shows that any span is a subspace. And then part two shows that any subspace can be written as a span. All right, so I want to show that span of S is a subspace. Just to make this proof more straightforward and easier to follow, I'm going to assume that I have a finite set S. The statement is true for infinite sets as well, but because we're not too comfortable with infinite sets and linear combinations of them, I'm going to just do the finite case. All right, so I want to prove it's a subspace, so I need to prove the three properties. Property one, I need to show that V is in the span of S. So that means I need to write 0 as a linear combination. So if you remember from the properties that we proved, 0 V1, 0 V2, and 0 times Vn, those are all 0V. All right, so if I add them up, I get a linear combination. I'm going to get the 0 of V n times, but if I add 0 by itself, that's V. If I add 0 and 0 and 0, I get 0V. All right, so 0 can be written as a linear combination of S, in fact, of any subset. And so, yes, 0V is a linear combination of S, and so 0V is in the span of S. All right, that's property one. In property two, I need to prove that if I take two elements of the span, so two vectors that are written as linear combination, so let's take V to be A1, V1, A2, V2, A and Vn, and let me take W to be, let's use B's, B1, V1, B2, V2, B and Vn. So those are any elements in span of S. Then the sum, that's going to give me A1 V1 plus AN Vn, B1 V1 plus BN Vn. Now, if I really wanted to be extra careful, I'd have to show you that I need to use associativity to change the parenthesizing of this statement. Then I need to use commutativity to move things past each other. But it'd be a bit complicated to write down, so let's just do it like we're used to doing it in R, but be aware of what you're using here. So here I can change the order of the terms and add all the things that have V1, all the things that have Vn together. Then I could use the distributivity and what I get is a real number times the vector, and so yes, V plus W is a linear combination of S, and so V plus W is in span of S. All right, final property. I'm going to take V in the span, so I can write it as a linear combination, and I'm going to take K in R. Then K times V is K times all of this. And if I distribute it, this is what I get, which is a linear combination. I get new constants here. And so, yes, K is in span of S. All right, so we've proven property 1, property 2, and property 3. Let me just make a tiny bit more space. I hate doing that because I know that if you're writing on paper, you cannot. But here, I've proved the 3 properties, and so span of S is indeed a subspace of V. All right, so that's the first part. We wanted to show that S is a subspace of V. We've done that. All right, it wasn't the end of that statement, though. I'm saying it is the smallest subspace of V which contains S. All right, so that means I have 2 more things to prove. I need to prove that it contains S, and I need to prove that it's smaller than all the other ones that contain S. All right, so I need to write the elements of S as inside the span of S. So I'm going to take VI. Then I need to write VI in terms of all the V1s through Vn. So I can write it as 1 times V1, Vi. Notice that here, that's axiom 10. All right, so throughout this proof, we use pretty much every axiom we have for vector spaces. And you can see why we asked all of these axioms right now. All right, and if I have to write it using all of them, I would write it as 0v1 plus 0vi minus 1 plus 1vi plus 0vi plus 1 plus 0vn. All right, so vi can be written as a linear combination of S, and so vi is in span of S. So really what I'm proving here is that every single element of S is inside span of S. That's exactly what this notation means. All right, so I want to show that it's the smallest. So I want to show that if I take any let's see, where is it? All right, so we will show now that S is the smallest subspace that contains S. So I'm going to take any subspace of V that contains S. I need to show that span of S is contained in W. All right, so I'm going to take any element in span of S, and I need to prove that it's in W. So take V, which is A1 V1 plus AN Vn in span of S. We need to show that V is in W. All right, so S is inside W. That means that V1, Vn are all in W. By property 3, of subspaces. W is a subspace, so I can use property 3 to show that A1V1 is in W, A2V2 is in W, and ANVN is in W as well. All right, so because of property 3, I can stretch these elements and still be in W, and then by property 2, I'll be able to add them. Sorry, I called it V. So V, which was A1V1 plus A2V2 plus ANVN is in W as well. All right, so yes, span of S is inside W. All right, so that concludes the proof of part 1. I've proven that the span of S was a subspace. I've also proven that it was the smallest subspace which contained S. Now we need to prove part 2. I need to show that for any subspace of V, then W can be written as span of S for some subset S. Well, we're going to be a bit tricky. I'm going to prove that W is the span of W. So it is indeed a span. All right, so I need to prove that W is equal to span of W. So I'm going to prove two things. When I want to prove that A is equal to B, I'll prove that A is a subset of B, and then B is a subset of A. All right, so let's prove first that W is inside span of W. Well, that's what we proved over here. For any set, S is inside span of S. All right, so by this one here, we get that W is in, all right. And then by 2, this one, I get that W is a subspace that contains W. But span of W is the smallest. That contains W. And so span of W has to be smaller or equal to W. Right, so putting these two together, that W is inside span of W and that span of W is inside W, what you get is that W and span of W are the same. All right, so this is especially nice because it tells you that if you already start with a subspace and you try to span it, you won't get any new elements. You'll just get the same subspace. All right, so the span is a nice subspace building machine. All right, the takeaway here is that all spans are subspaces and all subspaces are span, albeit not in a unique way, as the generating set S is not unique. Right? In most cases, we won't use W as a generating set. We'll find something smaller, something finite, hopefully, for most of them. All right, so that's it for this video. In the next video, we'll be looking at example 1.3.4. We'll be showing that following subset of subspaces.